We're continuing our discussion of the magnetic lift. In part A, we found the minimum current required to maintain equilibrium, and then in part B, we calculated the height above the ground for which we have, starting from h is equal to 0 from the vertical position, for which we have this application point of the tension being at the top. So that's basically calculated. We have calculated the maximum value of the height h. Now in part C, what is the net torque on the cylinder if h is between 0 and r? And what is the net torque on the cylinder if h is between r and h top? And we want to define a dimensionless parameter sigma to NIWB over mg and express all subsequent results in terms of sigma and other given quantities. Okay, so we calculated the minimum current and then we found that h top, the maximum value, is r times 1 plus pi over 2. Now in part C, let's set up our coordinate system again. So x is into the page, y is the vertical axis, so I hat cross j hat should be k hat, so our right hand rule tells us that z is in this direction. So compared to this figure here, so this I have rotated it so that x is into the page, which means I have rotated this so that I can see the side view. So I'm looking at it from the side view. All right. So with that, when I have h between 0 and r, this mass is hanging here. So there is the gravitational force mg, tension, and the tension here is making an angle theta with respect to the horizontal axis. And remember, the magnetic field is pointing down here. It's in minus j hat direction. And for the radius is equal to capital R, and if I call this distance h, this is r minus h here. So you can see that the magnetic moment is making this angle mu. So in order to not confuse with this h, maybe we should call this h prime, r minus h prime, because it's a different h. Now we can see the torque due to this magnetic moment and the torque due to the gravitational force. So let's start with the torque due to the gravitational force. The torque due to the gravitational force, torque G, will be equal to R cross mg. Now, R is the vector that connects our force to the rotation axis. So R is basically this vector here. So this is our vector R, and that has a magnitude capital R. And this vector R makes an angle theta with respect to this force. So we can see that this is going to be equal to the magnitude of R vector, which is capital R, magnitude of gravitational force mg, sine of the angle between them. And what is the direction here again, using the right hand rule? R cross with mg, you can see the right hand four fingers point in the direction of R, and then they're curled towards mg. The thumb points into the page, that's plus I hat direction. So this is in I hat direction. How about the torque due to the magnetic field? Well, that is given by the cross product of magnetic moment with the magnetic field. And let's look at the angle between the magnetic moment and the magnetic field. That is 180 minus theta, right? So this is going to be magnitude of the magnetic moment, which is 2RW, the area, total current NI, current times total current times the area, that's the magnetic moment, B, and sine of the angle between them, sine of pi minus theta. And what is the direction here for mu cross B? Using the right hand rule, you can see that the four fingers of the right hand point in the direction of mu. We curl the four fingers towards the magnetic field B. The thumb points out of the page, so the torque is in minus I hat direction. Okay, what is sine pi minus theta? It is sine pi cosine theta minus cosine pi sine theta. Sine pi is 0, cosine pi is minus 1. So this is equal to sine theta. All right. Now, why is the tension equal to mg here? The net force on the y-axis, let's say, is equal to 0, so that this mass is suspended. And tension is equal to mg. And the net torque due to the gravitational force and the magnetic field will be equal to the torque due to the gravitational acceleration, the gravitational force, that is mgr sine theta in I hat direction, and then I have minus 2rw nib sine theta in I hat direction. Now the question is, what is sine theta? So let's look at sine theta. Well, that's from this right triangle here. You can see this is capital R, this is capital R minus h prime. So this side will be capital R square minus parentheses R minus h prime parentheses squared, square root, using Pythagorean theorem. So sine theta will be R square minus R minus h prime square, square root, divided by R, and this will be equal to R square minus R square minus 2RH prime becomes plus 2H prime R, and plus H prime square becomes minus H prime square, H prime square, square root, divided by R. R squares will cancel. So this will be H prime 2R minus H prime over R, and we have the square root here. Now, so let's take a look at the relationship between this H prime and H. So when H is equal to 0, this is right at the bottom, and when H is equal to H prime, that will be actually this distance here. So I noticed that what I have called H prime is indeed equal to H. So note that H prime is equal to H. Okay, so with that discovery, I can now write my net torque. Net torque is H 2 capital R minus H square root divided by capital R. That is my sine theta here. And then I have mgr minus mgr minus 2RW NIB in I hat direction. Now remember, so first of all, these R's will cancel. And remember that I have defined sigma parameter as 2NI WB over mg. So basically 2NR NIWB, this is equal to sigma times mg. All right, so with that, my net torque becomes mg h 2 capital R minus h square root 1 minus sigma in I hat direction. Okay. Now in part D, we want to calculate the same torque for h greater than R. H greater than R less than h top. Okay, so now we have rotated it a little bit more. We are at this distance. And let's say that we have rotated it by an angle alpha here. Now the new angle between mu and magnetic field B is beta. So that beta plus alpha is equal to 90 degrees. And from the angular displacement of alpha here, we can see that this arc length is equal to R alpha. Now, what is the torque due to the gravitational force? This time, our tension is a tangential force, as I mentioned also in part A. Our R cross with mg, R cross with F, because the tension is equal to mg, the net force on the y-axis is equal to 0, tension is equal to mg. It is mg capital R, and in which direction is it? So if I look at this cross product, R cross with mg with the right hand, the thumb goes into the page, so this is in I hat direction again. What is the torque due to the magnetic field? It is mu cross with B. Now this is 2RW NIB, sine of the angle between them, sine beta, and this, remember, is in minus I hat direction. So let's check. Right hand forefingers pointing in the direction of the magnetic field, curl them towards the magnetic field. The thumb points out of the page in minus I hat direction. Okay, and at the same time, I can see that beta plus alpha should be equal to 90 degrees. So when I see sine beta, that is also equal to sine of 90 minus alpha. What is sine of 90 minus alpha? It is sine 90 cosine alpha minus cosine 90 sine alpha, and that's going to give me, because cosine 90 is 0 and sine 90 is 1, this will give me cosine alpha. So that's cosine alpha. So the net torque I see here is the mgr in I hat direction minus 2rw nib sine beta, which is equal to cosine alpha in I hat direction. Okay, and I also see that the total h value here is now r plus r alpha, the arc length. So this is the amount with which I have increased this mass more in order to reach this point. The similar argument was made to calculate in part B that h top is r times r pi r over 2 plus r. So the same thing is here, capital R plus capital R alpha is equal to h. So what I call alpha is h minus capital R divided by r. Okay, so the net torque I can write as mgr in I-hat direction minus 2r w nib magnetic moment cosine of alpha, but alpha is h minus capital R over r in I-hat direction. Now I have the sigma parameter, which is telling me 2niwb should be replaced with mg times sigma. So with that, here I'm substituting sigma times mg. I obtain my answer for the net torque to be mgr parentheses 1 minus sigma times cosine h over r minus 1 in I-hat direction. That's the net torque we see in this scenario. Okay, so we looked at two different scenarios. For h between 0 and r, as you can see from this figure, there is no wrapping when h is between 0 and r. So this distance that this has gone up is equal to h. And for that scenario, I look at this figure from the point of view, from this point of view, where x is going into the page, y is the vertical axis, and z must be pointing in this direction. I hat cross j hat is k hat. The torque for the gravitational force is r cross mg. The magnitude of vector r, which is capital R, magnitude of the force mg, sine of the angle between them, sine theta, in I-hat direction. The torque due to the magnetic field is mu cross b. Mu cross b, the right hand forefingers curl down, the thumb points out of the page in minus I-hat direction. And also, this is going to give me sine of pi minus theta, which is sine theta, as I have shown here. So the net torque is mgr sine theta minus 2rw nib sine theta, where sine theta can be read here to be this side divided by the hypotenuse, but this side is found by the Pythagorean theorem, square root of r squared minus parentheses r minus h parentheses squared. So that divided by r gives us sine theta. With the recognition that h prime here is equal to h, I can see the net torque, if I introduce the sigma definition here, is given by this expression. When there is wrapping, when h is greater than r, the value of h is now r plus r alpha. So why is that r alpha? Because the amount of wrapping here is the amount of increase in the height of the mass. The torque due to the gravitational force r cross mg. Now the tension is a tangential force. It's mgr in I-hat direction. The torque due to the magnetic field mu cross b is mu b sine beta, where sine beta is equal to cosine alpha from this geometry here. Alpha plus beta plus 90 degrees is 180. So the net torque is mgr minus 2rw nib cosine alpha in I-hat direction. And here I also recognize that since h is equal to r plus r alpha, alpha is h minus capital R over capital R. Substituting that for alpha, I find my final answer. Also substituting for 2niwb mg times sigma, I get this simplified answer for the net torque.